All right, so in the first part, in the first video for this section 3.3, we've only been talking about limits, and that's because we need the limits that we proved at the first part of that video in what we're about to do. So now we're ready to start looking at derivatives. And as we said at the beginning of this section, we really need to evaluate the derivative of sine and cosine first, because then the other four derivatives, the other four trigonometric functions, those will come naturally from this. So let's take a look at the derivative of our sine function. The derivative of sine of x, by definition, is the limit as h approaches 0 of sine of x plus h minus sine of x all over h. That's your definition of a derivative. In trigonometry, you cover a whole bunch of different identities, and among those is one called the sum identity for sine, cosine, and tangent. Those are identities that deal with expressions of this type: sine of something plus something. Okay. Now, if you need to, you can go. It's really easy to find, trigonometric identities, like big tables of them. This is one of the most common ones. If you're watching this on my YouTube channel, I've taught a full trigonometry class that's been recorded, and one of my videos derives this sum identity. So you can go look at that if you want. But assuming you know the sum identity for sine, which you should by the time you're in this class, sine of x plus h expands out to this: sine of x times cosine of h plus cosine of x times sine of h. And then here's my minus sign showing up again, all over h. Okay? So now that I've done this, I'm going to do a whole lot of manipulating with this quotient all in one step. So you notice I go from here to here. And what's happening here is I have this sine of x cosine of h here and a minus sine of x here. I'm going to group up both of those terms and factor the sine of x out. That leaves me with a cosine of h minus 1, which is showing up in the numerator here, all over h. Then what's left is cosine of x times sine of h over h, and I'm going to take the cosine of x and just bring it out to the front of that quotient. Okay, so now what I have is a sum of two products, and I can bring my limit into each factor of each of those products using my limit laws. So going through each one of these, the limit as h approaches 0 of sine of x, there is no h in that expression. So as we've seen before, this thing gets treated like a constant and is left alone. It just stays sine of x. Here is one of the limits that we proved in the previous video. The limit as h approaches 0 of cosine of h minus 1 over h. We showed that that limit was equal to 0. Now over here I have the limit as h approaches 0 of cosine of x. Once again, there is no h in that expression, so it stays cosine of x. And this limit right here, as h approaches 0 of sine of h over h, is the other limit that we proved in the previous video. We show that that's equal to 1. So this term goes away, there's a 0, and this term becomes cosine of x. And now we see that the derivative of the sine function is the cosine function. Now, if that seems super convenient, I agree. It is very convenient that the derivative of sine is cosine instead of some other crazy thing. But if you look at the graphs of those two functions, it shouldn't be too hard to see why that's the case. Remember, sine and cosine are both periodic functions, and one of these graphs looks identical to the other graph, just shifted to the right or to the left, depending on your perspective. So if we look at the function sine of x and compare it to its derivative, which is cosine of x, look at where the horizontal tangents are, first of all. So we'll just stay here for now, between 0 and 2 pi. Sine of x is going to have horizontal tangents at maximum and minimum values when it hits a high point or a low point. And we know from our sine of x function that pi over 2 is one of those places. Sine of pi over 2 is equal to 1, and that's the maximum value the sine function can take on. 3 pi over 2, sine of 3 pi over 2 is equal to negative 1. That's the lowest point that we can get to on this graph. So that would, based on the graph, you could see that that would correspond to another horizontal tangent. At both of these values, we would expect our derivative to equal 0, because remember, when your derivative is 0, that's where you get horizontal tangents like this. But we also know that cosine of pi over 2 is 0. And cosine of 3 pi over 2 is 0. So at least for these 2 points, we're seeing what we would expect. Now, beyond that, we also expect as we, if you go from 0 to 2 pi, for example, the sine function will be increasing from 0 to pi over 2. That's throughout the first quadrant. It's increasing, which means our derivative should be positive above the x-axis. We're seeing that with the cosine function. Then as we go from pi over 2 through pi to 3 pi over 2, that's working through quadrants 2 and 3 of the unit circle. And sine is negative, not negative, but sine is decreasing throughout those two quadrants. And we see that in the graph, decreasing, going downhill. So we're expecting that between pi over 2 and 3 pi over 2, all of our derivatives should be negative. And that's exactly what we see. It's all below the x-axis. It's all negative. Once we get to 3 pi over 2, we've established before the derivative is equal to 0 there. But then the sine function starts to increase away from that, which implies that our derivative should be positive. So the derivative, the cosine function, is positive everywhere where it would need to be positive, negative everywhere where it needs to be negative, and 0 everywhere where it needs to be 0. It starts to make sense graphically why cosine is the derivative of sine. Now that's not a good enough argument because, you know, I could achieve the same thing by making this wave much more boxy looking, you know, and still get all the same characteristics that I just described, but it wouldn't be cosine. So that argument is more just a suggestion that cosine makes sense. We prove that cosine is the derivative up here. Okay? Now, the next thing we would want to do is derive the derivative of the cosine function, but the approach would be essentially the exact same as what we did up here. Notice instead of having a sine here and here, I would have cosines here and here, and I would be using my sum identity for cosine instead of for sine. So this would look a little bit different, but the idea is the same. And then I would go through similar simplifications. I would see both of these limits show up again, and I would do basically the same thing. So even though, you know, it's not an identical proof, it's so similar to what we already did that I don't want to take the time to walk through it. If you did, though, you would see that the derivative of cosine of x is not sine of x, but negative sine of x. Okay, so we need to remember that. It's negative sine of x. Now that we have both of these results, that the derivative of sine is cosine and the derivative of cosine is sine, I can now find the derivatives of my other 4 trigonometric functions. I am not going to derive all 4 of them. I'm going to derive one of them and then let you find the derivatives of the other 3 on your own. Your book does a different one for you. It does the derivative of tangent. But the approach is so similar, and it's more instructive to try and do this yourself. I encourage you to try and derive these on your own. So we want to find the derivative of secant of x. I don't need the limit definition anymore, because this is the same thing. The derivative of secant of x is the same thing as the derivative of 1 over cosine of x, because that's what secant is, right? Now I can apply the quotient rule to this. So the quotient rule says, if I call this u and I call this v, I want v u prime. So that's cosine of x times the derivative of 1, which is 0, minus u v prime. So minus 1 times the derivative of cosine, which we just showed was negative sine of x, all over cosine squared, because it's v squared, so cosine squared of x. Simplifying things a bit, I have this term going to 0. Negative 1 times negative sine of x is equal to sine of x over cosine squared of x. And I could technically leave this alone. I could just say that this is the derivative of secant of x. But as you know from trigonometry, we like identities. We like to simplify expressions like this when possible. So notice that this expression could be rewritten as 1 over cosine of x times sine of x over cosine of x. See, I just took I took these 2 cosines and put 1 in each denominator there. My purpose behind doing this is because each of these is a trig function in its own right. 1 over cosine of x is secant of x. Sine of x over cosine of x is tangent of x. This is what we are typically going to say is the derivative of secant of x, as opposed to something like this. Okay? And you'll notice that's showing up right there. So here's a full table of the derivatives of your trigonometric functions. We proved 3 of them so far. The derivative of sine of x is cosine of x. Derivative of cosine is negative sine. Derivative of secant of x is secant of x tangent of x. Here's the other 3. I'm going to just state them for reference, but you could prove all of those in a similar way as what we did there. Derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. The derivative of cotangent is negative cosecant squared of x. You are going to need to memorize these, okay? And there are patterns present here if you're paying attention. So first of all, 3 out of your 6 trigonometric functions start with the word cosine, cosecant, cotangent. Notice that the ones that start with the word each of their derivatives comes out with a negative sign. Negative, negative, negative. That doesn't happen with the other 3. So one thing you can try and remember is that if I take the derivative of a trig function, it's going to have a negative sign. You're going to use the derivatives of sine and cosine so much that you're going to naturally memorize these. For the other ones, notice that each function has a corresponding co-function, so tangent and cotangent. Notice the results look very similar. Tangent has a derivative of secant squared. Cotangent has a derivative of negative cosecant squared. So the co-function that's showing up here, tangent and cotangent, their derivatives are corresponding co-functions, secant and cosecant, okay? Both of them being squared, and then we talked about the pattern with the negative here. Something similar happens with cosecant and secant. So when I take the derivative of secant and I get secant tangent, when I take the derivative of cosecant, each of these functions turns into their corresponding co-function. Secant of x becomes cosecant of x. Tangent of x becomes cotangent of x. And then there's the negative that we talked about before. So little things like that to keep in mind. That's going to help you memorize this stuff. All right, we're going to do a few examples here. So I want to find the 34th derivative of sine of x. Obviously, if I'm asking you for a derivative that's that high, you don't need to evaluate 34 derivatives. This is a question like this should make you think there's got to be some pattern that I can exploit here. So let's take a look first at the first few derivatives. If y equals sine of x, then y prime is equal to cosine of x. We established that. Y double prime is the derivative of cosine, which we showed was equal to negative sine of x. What would y triple prime be? Well, we know the derivative of sine of x, and then negative 1 times sine of x, I could use my constant multiple rule. It would just be negative 1 times the derivative of sine, or negative cosine of x. Similarly here, my 4th derivative is going to be negative 1 times the derivative of cosine, or negative 1 times negative sine, which is just sine. Notice we've ended up back where we started. So if I continued taking derivatives here, I'm just going to end up with the next thing in this list, cosine of x. And the 6th derivative is just going to be the next thing in that list, negative sine of x, and so on, right? So what we're seeing is a pattern or a cycle of 4 here. These derivatives, when you're dealing with derivatives of sine or cosine, no matter how many higher order derivatives you take, you only get one of these four functions as a result, and it's always going to be in the same sequence, cosine. So if we're starting with sine of x as our original function, then the first derivative gives me cosine, then negative sine, then negative cosine, and then sine. So using this pattern, what would the 34th derivative be? Well, I can see that every multiple of 4 is going to give me a sine of x. Because if I continued this, by the time I get to the 8th derivative of y, I would be back at sine of x again. 34 is not a multiple of 4, but 32 is. And if I were to divide 34 by 4, I would get 8, because that gives me 32 here. 8 times 4 is 32, with a remainder of 2. So again, once I've gotten to my 32nd derivative, I would be back at sine of x again. The remainder means I have 2 more derivatives to take, which gets me to negative sine of x. So that tells me that the 34th derivative is negative sine of x. This should feel very similar to when you deal with powers of I, when you are first introduced to complex numbers in algebra. Powers of I have a similar cycle of 4 pattern in them. Okay? Oh, I got a blank page in there. A couple blank pages. My printer has been doing this recently, giving me a bunch of blank pages. Let's remove those. Okay, so this is actually our last page. For what x values does the graph of y equals e to the x cosine of x have horizontal tangents? Remember, this is the same thing as asking for which x values is the derivative equal to 0. So we need to start by finding a derivative. Y prime is equal to what? I can see that I would need my product rule here. So I'm going to do my first function times the, let's actually do the derivative of the first times the second. So that would be e to the x cosine of x plus the derivative of the second function times the first function. Well, the derivative of the second function is negative sine of x. So I could write this as negative e to the x sine of x, like this, okay? Or I could factor the e to the x out and write that as cosine of x minus sine of x, okay? And we want to set that equal to 0. Now, e to the x can never equal 0. It's an exponential function. Those are never equal to 0. So by my 0 product rule, this would imply that cosine of x minus sine of x is equal to 0. Okay? Now, this is a trigonometric equation. You can solve this in a variety of different ways. What I'm going to do to solve this is let's actually take a kind of a unique approach now that I think about it. I could solve this using just algebra and working with trigonometric equations the way you learn in a trig class, but I'm going to do something a little bit more, I don't know if creative is the right word. I don't want to say creative, but just a little bit more outside the box. This is the same thing as saying cosine of x equals sine of x. Let's look at our unit circle for a second. Remember, cosine of x represents the x coordinate of a point on the unit circle. Sine of x represents the y coordinate. Well, where is the x and y coordinate the same? Any point at which the x or y coordinate of a point, any point for which the x and y coordinate are equal to each other would have to lie on the line y equals x, because that's where y and x are equal. That intersects the unit circle at only 2 points, root 2 over 2, root 2 over 2, and negative root 2 over 2, negative root 2 over 2, okay? But what is the corresponding x value for that? Because remember, we're looking at an angle here. Well, that would be pi over 4. That's what this angle is right here. And then if I do if I add pi to that, that would take me to this point here. And then if I add pi to that, it would take me to that there. And I can keep adding pi and getting angles for which this equation is true. So by saying plus pi k, that accounts for all other possible angles. Okay? All right, cool. I'm going to try and squeeze in one last example here. So this is one from physics. It says an object with a weight of capital W is dragged along a horizontal plane by a force acting along a rope that's attached to that object. If the rope makes an angle of theta with the plane, then the magnitude of the force is given by this. This mu here is called the coefficient of friction. Coefficient of friction. It is a constant, as is W. W is also a constant. So what we're talking about is some kind of object with a weight of W. There's a rope attached to this object, and it creates an angle of theta with the plane. And the object is being pulled by that rope, and some force is acting on that rope to pull in that way. This function here for this force is something you could derive in physics, but because this isn't a full-on physics class, we're not going to go through the derivation of this. Instead, we just want to deal with the question itself. So first thing it's asking for is the rate of change in f with respect to theta. Okay, so what we're asking about is this, df d theta. Now, again, mu is a constant, w is a constant. Theta is the variable here. So we want to use the quotient rule to evaluate this derivative. I want my function on the bottom, which is my v, times u prime. But remember, u is a constant. So I would end up with this, mu times sine of theta plus cosine of theta, times the derivative of this constant, which is 0. That whole thing is going to go away. Minus the numerator times the derivative of my denominator. Mu w times the derivative of this, which would be mu, it's a constant, derivative of sine is cosine of theta. Derivative of cosine is minus sine of theta, all over that numerator squared. Mu sine of theta plus cosine of theta. Let's simplify that a bit. This is going to simplify down. I can bring that negative in here, and all that's going to do is switch these two terms around. So I'm going to have mu w over, mu w times sine of theta minus mu cosine of theta over mu sine of theta plus cosine of theta. Okay, so this, I could just leave this in this form. I might be able to do some simplification with some trig identities or something, but I'm not going to worry about that. I've found my rate of change. What do I need to do now? I need to determine when this rate of change is equal to 0. Remember, when a rate of change is equal to 0, that implies that the function is constant. It implies a horizontal tangent if we're looking at the graph, but it also implies that there's no increasing or decreasing trend. We're actually going to prove that more thoroughly later. But if I were to set this thing equal to 0, then that implies that my numerator is equal to 0. Now, I didn't state this, but the coefficient of friction is a non-zero quantity, and the weight is also non-zero, because we have an object. It has to have some weight. So to set this thing equal to 0 would imply that the stuff in parentheses here is equal to 0. This implies that sine of theta minus mu cosine of theta equals 0. But if I were to add this term over and then divide by the cosine, this would imply that mu is equal to sine of theta over cosine of theta, which is the same thing as tangent of theta. Okay? So this rate of change is equal to 0 when tangent of theta is equal to mu, or to solve for theta explicitly, when theta is equal to the inverse tangent of mu. Okay? I'm off the screen there. So this is a useful little thing in the context of this physics problem. If we need to know when our rate of change is 0, which means when our force is acting as a constant, that will occur when the inverse tangent of our coefficient of friction is the angle that we're acting on. Okay? Again, if you haven't been through physics, this might feel like a weird, kind of a weird concept, because there's some background knowledge that helps you understand this a little bit more. But we can still solve a problem like this working directly with what we're given. And now that we know the derivatives of sine and cosine, this is a doable type of problem. But this is going to wrap things up for us for section 3.3.